Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about S-type instructions, where we have discussed about R-type instructions and I-type instructions. So in this particular video, let's continue with the S-type instructions. Now, basically, S-type instructions are basically used for storing the data into memory. So let us let us try to understand how this is S-type instruction and what is the field encoding and all. So we have basically six type of instructions, and now we are discussing about S type instructions. Now this particular S type instructions write a value from a register into the memory. So we are going to take the value which is present inside my register, and that I'm going to store it into the memory. And these are basically store instructions. So unlike R type instructions and I type instructions, where we use it to have something known as destination register in the case of my R type instructions and I type instructions. But in the case of my S type instructions, I am not going to have any kind of destination register. My destination is a memory. Okay. Now, it needs two registers. One is RS1 and another is RS2. Now, RS1 is going to store the base address. Okay. And where RS2 is going to store the value which I need to store into my memory. Okay, so RS1 is going to hold the base address, and RS2 is going to hold the data which I am willing to store into my memory. Now, this I'm also going to have something known as 12-bit immediate. So let me show you the instruction first. Yeah, this is my instruction which I'm going to have, which is an S-type instruction, and you can see the opcode is fixed. So if you take R-type instruction or I-type instruction or S-type instruction, opcode is 6 down to 0, and I'm going to have function 3 14 down to 12 bits. So this is my function 3, and immediate is being split into two different fields. This is immediate 4 down to 0, which is 11 down to 7, and immediate 11 down to 5, which is present in 31 down to 25. Okay, so basically immediate is from 11 down to 0, which is total 12 bits. We are going to have a 12-bit immediate value that is being split into two different positions, one at 31 down to 25 and another at 11 down to 7. Now, what is this 12-bit immediate used for? This 12-bit immediate is used for calculating the offset address. Now, what do I mean by this offset address? As we have seen, RS1 is going to store the base address. So RS1 is going to store the base address. And what do you mean by base address? Suppose if we have a memory like this, and the base address is nothing but my starting address, which I want to have the start. Okay, this is, let's say this is my base address. Now offset address is nothing but from this particular base address, what is the location you want to access? Let's say suppose after 1, 2, 3, 4 locations, this location I want to access, then my offset address will be equal to 4. So this offset address will be stored inside your 12-bit immediate. You are going to provide the immediate offset address. You are going to provide the offset using this particular immediate field. Okay, that is the use case of using my offset address. So 12-bit immediate encodes a byte offset added to RS1. So we are going to add it to the base address to form the entire memory address. And because there is no destination register, the space the field would occupy is reused and split across the immediate. So since we don't have a destination register over here, the space which was occupied by the destination register, we are using it for splitting my immediate field over here. Okay. Now, so you can see the instruction over here, mem of rs1 plus immediate, and this is my data which I want to store. rs2 is going to have the data which I want to store, and how you're going to calculate the address, it is calculated by base address plus offset address. So address plus offset address, after we have calculated whatever the address we need to store my data, that particular data will be holding in my rs2, that will be stored inside the memory location which we have specified using this particular rs1 plus immediate value. Okay. So this is my h-type bit layout, where we have already seen like what are the different kind of fields, and this is also a 32-bit instruction. So opcode is basically going to decide what kind of instruction it is, whether it is an R type instruction or whether it is an I type instruction or whether it is an S type instruction or whatever the 6 instructions we have, right? For differentiating my instructions, I'm going to use this opcode, which is going to help me to find exactly what kind of instruction it is. And as I've said you, immediate 4 down to 0, whole immediate 12-bit value is used for representing my offset, where the 5-bit value it is going to use, lower 5-bit value, it is represented using this immediate 4 down to 0, and upper 7-bit value is a 12-bit signed byte offset. Okay, suppose if we have an offset address as 8, so here 8 will be represented as 12-bit signed immediate value, 12-bit signed immediate value. Now this 12-bit signed immediate value, lower 5 bits will be stored inside this particular field, lower 5 bits will be stored inside this particular field, and upper byte will be stored inside my immediate 11 down to 5. So upper byte will be stored over here, and whatever the upper byte we are going to have, right, this will be signed. Okay, so this is how we are going to store my 12-bit signed immediate value across two fields, where immediate 11 down to 5 is high 7 bits of 12-bit signed byte offset. Okay, and my lower bits are going to be represented using lower 5 bits, they are going to be represented. Okay, sorry, not this is basically 7 bits. This is basically 7 bits, and this is basically 5 bits. Okay. Now, and coming to function 3. So what is function 3 going to tell us? It is basically of 3 bits. So function 3 is going to tell me what kind of operation in the step you want to perform, whether you want to store a byte, or whether you want to store a half word, or whether you want to store a word, or whether you want to store a double word. So this function 3 is going to tell me. Using this function 3, we are going to decide like what kind of store operation we need to do, like what kind of information I want to store in my memory. And next is RS1. As I've already told you, RS1 is the base address which we are going to mention, and RS2 is going to have the data which I want to store into my memory. And offset is represented using the immediate value. And why we are going to split the immediate? So because RISC-V decoder is always going to read the RS1 from 19 down to 5 and RS2 from 24 down to 20. Irrespective of whatever the instruction you're going to use, you can see in the R type instruction also, RS2 and RS1 positions are fixed. And you can see in the S type instructions also, RS2 and RS1 is fixed. So it will be easier when decoder is going to decode this particular instruction, because if these positions are fixed, the decoder it's very easier to decode this particular positions. That's the reason whatever the kind of instruction you're going to use, irrespective of what kind of instruction you're going to use, your RS2 and RS1 positions are fixed. Okay, so that's the reason we are going to split the 12-bit immediate value in the S type instructions in two particular fields. Now, since this particular two immediate value is being split into two particular fields, we are going to concatenate them, and we are going to form a 12-bit immediate value. So we are going to concatenate immediate 11 down to 5 and immediate 4 down to 0. And whatever the 12-bit immediate value we have got, that I am going to sign extend it to 32-bit value. So whatever the immediate 12-bit value I am going to have after concatenating, I'm going to perform the sign extension on this, and I'm going to convert it into a 32-bit sign extended value. Now, what do you mean by sign extended value? So sign extended value over here, if we can see, let's say suppose if this is my 12-bit sign extended 12-bit offset address 110101 1 1 2 3 4 5 6 7 8 9 10 11 12. Let's say if this is my 12-bit offset address and it's a signed value. Okay, so my offset address can be a positive value or it's a negative value also. If it's a positive value, it is represented directly, but if it's a negative value, it is represented in sign format. Okay, now let's say if this is my sign negative value, and you can see your MSB is equal to 1, right? If you are going to sign extend it, you are going to fill MSBs to ones, and you're going to convert it into a 32-bit value. But if your MSB is equal to 0, you're going to copy zeros only into your further MSB bits, and you're going to form a 32-bit value. That is nothing but my sign extension. So negative offsets, I can also have negative offsets. That's the reason I'm going to perform sign extension over here. Now, what is function 3 going to do? So as I would said you, function 3 is going to decide whether it is a store byte operation or if it is equal to 001, function 3 value if it is equal to 001, it is a store half word instruction, or if it is equal to 010, I'm going to decide whether it is a store word instruction, or if it is 011, I'm going to decide whether it is store double word instruction. So depending upon the function 3 value, I'm going to decide what kind of operation it is going to have. And store double word is only used when I'm going to use RV64. RV32, it is not going to have store double word, it is going to stop at store word itself. Now, what is that we are going to do in store byte? So it is going to take the relevant low bits of register RS2 and writes them to memory at address which is generated using RS1 plus sign extended immediate value, and storing exactly 8 bits, that is 1 byte, into my memory. So this is my store byte instruction. You can see over here SB RS2 immediate of RS1. This is the instruction which I'm going to have, and RS2 is going to store the data which I'm going to have, and RS1 is going to have the base address, and immediate is nothing but it is having the offset address. So after mentioning this, it is going to store this particular data into the base plus offset address. And you can see over here only the least significant byte of RS2 is written. So RS2, if you have remembered, we have discussed in our previous sessions also, RS2 is a 32-bit register, right? But over here in the 32-bit register, from this 32-bit register, I'm only going to take the least significant byte of data, and I'm going to store it into the memory which was specified, into the memory address which was specified. Now, in the case of my store half word, I'm going to store a half word in my memory. So what is that? I'm going to have function 3001, and the syntax is sh rs2 immediate of rs1. So rs2 is again a 32-bit register. From this 32-bit register, I'm going to consider last 2 bytes of data, and I'm going to store into the address which was specified by rs1 plus immediate location. And in the store word, I'm going to directly have all the 4 bytes of data, and I'm going to store it into the address which was specified in this particular instruction. And store double word, I'm going to basically not have any kind of store word instructions in my RV32 base instructions, because all the registers are of only 30 bits, right? Yes. So let's see one example. So let's say suppose if I'm going to have store word x5 8 x6. So that means this x5 is having the data which I want to store, and x6 is having my base address, and 8 is my offset address. So what I'm going to do, I'm going to have the opcode as this, and base address is going to stored in x6, that is my rs1, and offset address is and my rs2 is nothing but my data which I want to store, which is being stored in x5, and function 3 is telling me that it is a store word instruction and the offset address is 8. So using this information, this is how I'm going to encode the data, and this is my assembly instruction or the binary instruction I'm going to have. And in hexadecimal, this is how you're going to look like your instruction. Okay. So you can see immediate value is being split across the two fields over here, and this is my opcode which I'm going to have for this store word instruction, and function 3 is this, and I'm going to have rs1 and rs2. So this is how I'm going to have the instruction. And we have already seen how we are going to compute the instruction rs1 plus immediate, which I'm going to get the address, and into that particular address location I'm going to store my data. Now, let us compare our S-type instruction and I-type instruction. Whereas in the case of my S-type instruction, I'm going to store the data into my memory, which is present inside my register RS2. But in the case of my I-type instruction, I'm going to store the resultant into my destination register. And here we are going to have two register reads, RS1 and RS2. There is no RD. And in the case of my I-type instruction, I'm going to have only one register read, which is nothing but my RS1, and one write, that is nothing but my destination register. So here in the case of my I-type instruction, I'm going to have one read and one write, whereas in the case of my S-type instruction, I'm not going to have any kind of uh, write operations into my into my registers. I'm going to have only read operations into my registers. So where can store instructions can be used? It can be used in functions, or it can be used in register spilling, or it can be used when we are dealing with arrays and structs, or if we're dealing with memory mapped IOs. So this is about our H-type instructions, where we have discussed about all kind of H-type instructions and how the instruction format is. This is very important if we want to build a RISC-V processor. Uh, Whenever we are trying to develop the Verilog code, we need to have the instruction encoding and all, so that we can follow them and we can build our code. Yes. So that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.